That's good. All right, so folks, let's get started with some questions, which is for review from last time. So it says the capacitance of a spherical capacitor depends upon A, radius of the inner and outer spherical surfaces, charge on the spherical surfaces, potential difference between the two surfaces, all of the above, none of the above. Please talk to a person next to you. You have 1 minute to answer this question. All right, folks, the correct answer here is A. It looks like most of you got it right. And that is because if you remember, capacitance is a property of the capacitor, right? So it depends upon, say, for example, the radius RA and RB of the inner and outer cylinder. So if you have one metal plate like this and the other one like this, so these are two metal plates. These are spherical plates or conducting plates. And suppose you have positive charge here plus Q, and here you have, say, like, let's say negative charge minus Q. You know that there's going to be a potential difference here, right? Potential difference delta V, or we are starting to call it V now with the understanding that this is delta V. Another way to say it is that there is an electric field, because whenever there is an electric field there will be a potential difference. But what we understand is that Q is equal to C times V, and so C is Q divided by V, and this is a constant, you know, which only depends upon these radii, R's of A and R's of B, and it will depend upon whether you have some dielectric here or whether you have air. Remember, there was a kappa, but it will not depend upon Q or V. Why? Because if you increase the voltage, the charge on the plates will increase such that Q over V is constant, right? Because C is a constant, and that's the important thing to remember. All right, so let's move on. Is everybody clear that C is a constant which only depends upon the geometric properties? Let's look at this. Which one of the following is an appropriate unit for the quantity epsilon 0 times E square? You're given 4 choices. You have 1 minute to answer this. Please talk to a person next to you. All right, folks, if you remember the energy density, that means the energy stored per unit volume. This is the energy per unit volume in the electric field, say for example between the plates of a parallel plate capacitor or between the plates of a cylindrical capacitor. If you want to know how much is the energy per unit volume, that energy turns out to be half epsilon 0 E square. So obviously the unit of this thing should be joules per meter cubed, because joules is the unit of energy, and the unit of volume is meter cubed, the SI unit. And so half is unitless. So the point is that the unit of epsilon 0 times E square is definitely joules per meter cubed. Is everybody seeing that the answer is joules per meter cubed? Right? Because half does not have a unit. And we said that the energy stored in the if the electric field is E, then the energy stored per unit volume is half epsilon 0 E square. All right, let's move on to the next question. Is there any question about this? All right, here the question says, consider a capacitor made of two parallel metallic plates separated by a distance d. The top plate has a surface charge density plus sigma, the bottom one has minus sigma. A slab of metal of thickness L less than d is inserted between the plates, not connected to either one. Upon insertion of the metal slab, the potential difference between the plates, what happened to the potential difference? So the question is this: you have two metal plates, one of them has charge density plus sigma. Sigma is the charge per unit area. Here you have minus sigma. And the question is asking, initially it's like this and you have some electric field here. The question is asking, if you insert something here, let's say a metal plate, not touching either of the two plates, you're not touching it. The question is, what do you think will happen to the potential difference between the plates? All right, 1 minute to answer. Please talk to a person next to you. Is everybody understanding that the metal plate that you insert is not touching either of the plates, right? Okay, go ahead. Please talk to a person next to you. 15 seconds. All right, if you think about it, oh wow, this is a problem in which people got very different answers. See, here is the thing. Sorry. What you have to think about is the fact that, is this very similar to what we talked about for dielectrics? It is, except that will the metal be more extreme than a dielectric? It will be, because in a dielectric, you have just a little bit of polarization, right? Here, what do you think will happen? If this is a metal plate, would you expect that the electrons from this surface will literally go and they'll come here to this surface, negative will accumulate there? Wouldn't you? And they'll leave behind positives on this surface. Would you think that way? So if suppose the external electric field, let's call it E external, E external is basically the electric field in vacuum, right? That would be, for example, remember electric field was just nothing but sigma over epsilon 0 between the plates. This is the E external, or you can call it E vacuum if you like. Now, which way is the electric field due to the charges that are induced on the surface of this conductor? Is it in the opposite direction? Yes. If you see, electric field points from positive to negative. So the electric field, this you can call, if you like, internal electric field. So does everybody see that the external electric field due to the charges on the plate and the internal electric field that is due to the induced charges, they are pointing in opposite directions? So if you think about the net electric field in this region, wouldn't it be less? And if the net electric field is less, the potential difference between the plates is lower too, right? Because electric field is related to potential difference. Is everybody agreeing with that? So the correct answer here is B. It decreases, right? In fact, this effect is going to be much more dramatic than the effect with a dielectric, please.
Is the E internal inside the metal plate?
Sorry?
The E internal? Is it
No, actually that is a good, that is a very good, sorry. So let me explain. So yes, there is an E internal like this, right? And the thing is, since this is a metal plate, what will happen is that inside the metal plate, the E net becomes 0. That's a very, very good point. So the point is that the net effect of E internal and E external inside the metal would be such that the electric field becomes 0 everywhere, right? There in that region, right? So in this case, there is an extreme situation where inside the metal, so compare this with, the other thing you could have done would have been you would put a wood slab, right? If you had put a wood slab, what would happen is that at the level of atoms, since this is positive, the electrons will get a little bit closer to that side, right? At the level of atoms. So if you think about E internal is again pointing from positive to negative. So E net is lower, but it's not 0 in this material here, because this is an insulator, right? And the thing is, electric field is not going to be 0 here, but it's going to be lower than just this external electric field. Is that making sense? But in that case, the effect is very dramatic. In fact, the electric field inside the conductor becomes 0. Right? Okay. All right, let's move on. Okay, this is it. All right, so let's move on today. And in fact, we are going to completely switch gears today. What do I mean by completely switch? Please. Just a second. Sorry, go ahead, please.
What were you saying about the E net, that it's lower in both when they're both present?
What I'm saying is that E internal is always going to oppose. Sorry, what I meant is E internal is always going to oppose the external electric field, but there won't be a net cancellation inside the wood. It would be lower, but not 0. In the other case, it is going to.
Then why does the for the wood one, why does the potential difference go up, but the other one goes down?
No, so for wood also the potential difference. First of all, by the way, was the question asking what would be the potential difference across the plates of the capacitor? It was, right? So in both cases, do you see the same kind of effect is happening? If it was asking you what would be the potential difference anywhere inside the metal, inside the metal itself there won't be any potential difference, right? Because the thing is, if the electric field is 0, the potential is constant, right? But what I'm trying to say is that if you look at this effect, it's a much bigger effect because it's a macroscopic separation of charge, but the internal field is still that way, and it's opposing the external field which is acting down. Just like here, the internal field is going to be this way because positive is. Do you see that the effects are in the same direction? What I'm saying is that due to these induced charges here, the electric field in this wood is not going to be 0. It's going to be lower, right? In this case, inside the metal, it will be 0. But notice that these induced charges are also going to change things in these regions, right? And both of these are conspiring to do things in the same direction because the separations are all happening, in the same way. Just that the effect is at the microscopic level here, and here it's very big. Please.
So if you insert a piece of wood, say this has like a set amount of voltage, and then when you compare that to the piece of metal inserted, will the piece of metal decrease the voltage more than the wood?
Okay, that's a good point. Okay, one of the things that you have to remember is this. Remember what I said to you earlier. Q is equal to CV, right? In these cases, the case that I gave you there, in the case that I gave you, Q was fixed. So this thing is not connected to a battery or anything. That is an important thing. So the point that you're trying to make is a very important one. So there are two separate cases. You know, the cases that we are talking about here are cases where Q is fixed. By Q I mean this. That is fixed. And that's a very important point, because if Q is fixed and your C is changing, do you see that V must change to compensate, to keep this product the same? And that is what we are saying. We are saying that when you put these things in, you are actually increasing the capacitance, and therefore you would actually decrease the V. You know, there was a separate situation that we had talked about last time. So last time we talked about a situation like this, you know, where this is connected to, say, a battery. You know, let's say that this is a 3-volt battery that it's connected to, right? So initially I have this situation, and let's say now I insert a wood piece or a metal piece. Let's say we insert a wood piece. If I keep the battery connected, what do you think is going to happen as soon as I shove the wood in? So initially there was no wood, right? And then now I'm shoving the wood piece in. What do you think will happen? Yeah, because do you see that, you know, initially there will be a very short time in which there will be some movement of these charges, because putting the wood piece changes C, right? It changes C. And if it changes C, you know, somehow Q over V, you know, Q is equal to C times V. If C changes, there is a problem. You know, one of these two things has to change. Now we know that if this is connected to a battery, right, the thing is the voltage across this will finally come to, will always be 3 volt if I'm not disconnecting the battery, right? And that means what will change in this case will be Q. So if this is fixed because a battery is connected, so the battery is left there, then Q will change. And in this case, if C increases, Q will increase. So what will happen is, as soon as I shove this wood piece in, if I put the wood here, you know, initially let's say we had charge, you know, without the wood, let's say we had some charge Q and minus Q. As soon as I shove the wood in, you know, more electrons will go from here to here, such that we will accumulate some extra thing here, so that the charge here, you know, will become something like Q prime, and here it will be, you know, so minus Q prime, and here it will be plus Q prime. Does that make sense? Such that Q still becomes equal to C times V, because V has stayed 3 volts. If I'm using the same battery, V has stayed 3 volts. So if I increase C by a certain amount, Q must increase by the same amount to make sure that Q is equal to CV. Does that make sense? This situation? Okay, so this was a situation in which the charge was kept fixed. Right, folks? Here I didn't have a battery connected to this thing. So the charge on these plates is always fixed. And so the voltage is the one that's going to change if I insert things in. Any questions about this? All right, so then right now we are actually going to make a huge switch in the sense that all of the chapters that we have covered so far have been about electrostatics. What do I mean by that? We have always been interested in what happens, you know, even if initially for a short time charges may move, we are saying, you know, these charges might move. We are really interested in the situation where you have equilibrium, right? Once equilibrium is established, then what happens? Then what is the situation? That's what we have been interested in all this time. This is why we call it electrostatics, charges at rest. Now, from now on, we are going to talk about what is called current electricity. We are staying with electricity for some more time. But now we are going to talk about charges in motion. You know, and you are really familiar with this situation. You know, you played with those, you know, fix it, and I don't know, there are all those toys that show where you can connect different things in a circuit and you can see the flow of current, because once a current is flowing, that is not an equilibrium situation. Do you see what I'm saying? And so in that case, you don't have to have, say for example, the electric field inside a wire or something be 0, because we are not talking about an electrostatic situation anymore. We are talking about charges moving around and accelerating because there might be a potential difference, right? So we are really interested in the situation in which charges are moving. So the first thing that we need to define now is what is the meaning of the word current. Does anybody know how scientifically the word current is defined? Because everybody has heard this word, used this word all the time. How is it defined in science? Current has a very well-defined meaning. You know, you cannot use it in an imprecise manner. It has a special meaning. What is the meaning of current? Any thoughts? Please. Current is definitely due to moving electrons. There's no doubt. I mean, in most materials, you know, it's the electrons that do the moving. We said, you know, ions are at rest, right? So the electrons are the ones that are free to move in metals. So the current will flow in metals. So yes, it definitely is related to the motion of electrons in conductors or metals. But exactly how is it defined? Okay, good. I think all of you are saying very nice things. Go ahead, please. Yeah, it turns out that the precise definition is exactly what he said, which is it is the amount of charge that flows through any cross section, say for example of this wire, per second. So we can define the current like this. So let's say that this is my wire. And whenever I say wire, you know, it means it's a conductor. So there are free electrons in this wire. So let's say that, you know, we use the symbol I for current. And the thing is, current I is defined as dq over dt. That means it's the derivative of charge per unit time. So how much charge moves through any cross section. So if this is a wire, and look, if I cut this wire, this is going to be its cross section. Let's say it's a circular wire. So this is the cross sectional area is A, right? If I cut this out, current is how much charge. You know, there are these electrons moving. So if the current is flowing in one direction, do you know which way the electrons are moving? In the opposite direction. So it turns out that the convention that we have chosen, and this is because of history, and it doesn't really matter. Because it turns out you already know that if the current is flowing in a circuit, so for example I have a circuit like this. This is my battery. Let's say it's a 3-volt battery. As soon as I close the circuit here, there will be a current flowing. What we know, what you have already learned is that the electrons will be moving this way, right? Haven't you learned that? Electrons will move from the negative towards the positive. It turns out that what we call current is how much is the charge of the electron that moves every second, but we define a conventional current as flowing opposite to the direction in which the electrons are moving. So the current will be flowing opposite, and it really doesn't matter. This is not an important point. This is just a convention, because in olden times people used to think that current might be due to flow of positive charges, and so they chose that convention. We'll stick with this convention just for consistency, but I'm telling you, so long as you choose one consistent notation and move with it, it's not a problem, all right? Now, so what I told you is that if you cut this wire, and I have blown up this wire into this fat looking thing here, basically it's the same little wire I just zoomed in. And you can see if I cut it, the point is if the current is flowing this way, that means the electrons must be moving this way. And the question is, how many electrons are moving every second through one cross section? That would be called current. Not how many electrons, how much is the charge of the electrons, right? So Q, what is Q? Q will be the charge of one electron times the total number of electrons. Is that making sense? So this is number of free electrons. And this is the charge on one free electron. So dq over dt is current. Now what would be the SI unit of current? Somebody from the front row. If this is the definition of current, I don't want some hi-fi names. Please look at this definition and tell me what should be the SI unit of current. Look at this. Go ahead, please. Excellent. It should be the unit of current should be the unit of charge divided by the unit of time. So that is coulombs per second, right? And that has a shorter name. We call it ampere. After the scientist who did a lot of work, ampere was the last name of a scientist who did a lot of work in this area. So the SI unit of current is ampere, and it's denoted with a symbol A. And this is nothing so 1 ampere is equal to 1 coulomb per second. Any questions about this, folks? Okay, since I told you that really current is about, if I cut this cross section and there was a current flowing here, there were electrons moving here, we are trying to figure out how much is the total charge of the electron that is flowing through each cross section. Let's define something called current density. Current density would be current per unit area, right? In general, so let's now define a new thing called current density. And this will be denoted with the symbol J. Okay? And we can define the current as related to current density like this. J dot dA, integral over the whole area. Integral over the whole area of cross section. Okay, so you can see current density is a vector, but current is really a scalar quantity. It's true that current again can turn out to be positive or negative, but it doesn't, you don't say current is pointing 30 degrees south of west or north of east or something. A scalar quantity can be negative also, right? So current is negative, but current density is positive. And if suppose, if J magnitude is constant and is perpendicular to dA, what can we do? So what am I trying to say right now? Let me look at this picture here. Here is a case where, let's say this arrow here, my arrow here is showing the direction of current in this wire, all right? What I'm saying is, by the way, which way will be the area vector, dA? Is it perpendicular to the area? So if this is my cross-sectional area, if I cut this wire, and I ask, oh, there is this little circular thing, very, very narrow, this is very narrow, right? Wouldn't you say area vector is perpendicular to the surface area? Right? So is everybody agreeing that if this is the area, the vector dA is going to be perpendicular to the area, the direction, right? And now what I'm trying to say, if dA and the current density are in the same direction, then do you see that when I say I is equal to integral J dA times cosine theta will be 0 if the current density and area vector, so if the current density is also in the same direction and dA as dA, this angle will be cosine 0. So if J is constant and it's perpendicular to dA, sorry, but I don't really mean perpendicular, I mean parallel. So that means J and dA are both pointing in the same direction, then I have this as J dA times cosine 0 degrees. And if J is constant, J can be pulled out. So if, folks, there shouldn't be any talking. So J can be pulled out, and then this becomes J times integral dA. And what is integral dA? Is that just the area of cross section of this wire in which the current is flowing? Yeah, that's just A. So basically what we find then is this. We find that I is equal to J times A, the total area, right? And this means that I can write current density J magnitude as I divided by A. This is the total area of cross section. What should be the SI unit of current density? The unit of current divided by the current of area, right? So SI unit of J is ampere per meter square. Is that making sense, folks? Any questions about this? All right, then now we are going to talk about something called drift velocity. So I keep defining these new terms. Anybody knows how drift velocity is defined? Because maybe you have learned these things in some other courses. Okay, so then what is the picture that you should have in your mind about what happens when you connect a wire, say for example, to a battery? So in other words, you are connecting a conductor to a battery. So we have something that is like this. And let's say here is a switch. This is my battery. Let's say it's a 9-volt battery. As soon as I close the switch, is everybody agreeing that as soon as I close the switch, the electrons start feeling a force, right? And they start moving this way. And then we say, okay, this flow of electron is really what constitutes a current. But our convention will be that the current will be flowing opposite to the direction in which the electrons are actually moving. This is just a convention. Okay? But really when we say current is defined as dq over dt, that charge is really the charge of the electrons that is moving through any cross section every second. Is that making sense? Okay, so now if this is the current, is everybody seeing why are these electrons moving? Are they feeling a force? Are they accelerating? Well, they are feeling a force because of this battery, right? The battery has a potential difference. Potential difference means there must be an electric field. That electric field exerts a force on the electrons, and the electrons start to accelerate, you know, from the negative to the positive of the battery, right? Okay, so electrons are definitely moving. Now you might think, let's zoom in again on this wire here and think about what really happens when the electrons are trying to move in this wire. It turns out with a say 3-volt battery or 9-volt battery, these electrons, the force that the electrons could really speed up and move really fast. So electrons could even move as fast as say 10⁶ meters per second. So very, very fast speed. But do you think that's the speed with which they are moving through the wire? The answer is no. On an average, the electrons are moving extremely slowly, extremely slowly. In fact, if you have a 1 ampere current flowing in a wire, 1 ampere is a very large current, by the way. If you have a 1 ampere current flowing in a wire, it turns out the electrons in that wire would have moved by say 1/3 of a meter in 1 hour. So very, very slowly electrons are drifting in the wire. So these two things don't make sense. So I'm telling you, well, actually the electrons could move as fast as 10⁶ meters per second, but the electrons are actually moving very slowly, and they're moving so slowly that with a 1 ampere current, which is a huge current, they move only 1/3 of a meter in 1 hour. How can these two things be consistent? What is stopping them? Can you think of what might be stopping them from really moving forward? Go ahead. And the more important thing, that's a very good point, they run into the ions. You know, it's like if suppose I was running really fast, suppose there was a stampede or, you know, there was some fire or something in this room, we were all trying to run towards the door at the same time, right? So we were all feeling a force to, you know, that was propelling us. It's maybe an internal force, but we are all propelled in that direction. If suppose there are things in the middle, we could bump into that. So even though we are trying to run really fast, that's not the speed with which we are going to arrive there, you know, because we have to keep moving back when we bump into something. Then we move forward, we bump into another thing, and then we have to move back, you know. Then there's another thing, you know, it could be even other people that you're bumping into, other things that you're bumping into. And so because of this bumping, the actual speed with which the thing will go from here to the door is going to be, the actual speed will be much slower, right? Because the actual speed you can find, which is what we call the drift speed in this case, will be the distance traveled divided by the time taken to reach from here to there, for example. That would be the average speed, right? And that would be called drift speed. So what I'm trying to say is that if you look at the picture like this, these electrons, this is my cross section of the wire, and let's say that the electrons are trying to move in this direction because they are feeling a force due to this battery. So they're trying to move. I'm trying to blow up this picture here. This is my wire. What happens is that the electrons are running into ions, let's say. So this electron is wanting to move, then it bumps. Then there's another ion here, it moves forward. Then there's, it moves forward like this. Then there's another ion here, it bumps back. Again, it moves forward. Then it again, gets bumped. On an average, it will still be drifting this way. You see what I'm saying? So here it gets bumped here. Now here it comes here. Then over here it gets bumped into this ion, it moves this way. Here again it gets bumped like this. Then it gets bumped like this, etc. The point is the electron is not going to follow a simple path, but it will be a zigzag path because of the fact that it's bumping into so many ions in this material, in this metal, right? Is everybody appreciating what the problem is? So even though between these collisions, the speed is very large, so the speed of electrons is, very large, let's say 10 to the power 6 meters per second or something, say for example in copper, which is a very good conductor, in good conductors, good metals, if you are really saying, okay, I am only interested in knowing on an average how much time does it take for it to move this way, that's what we are calling the drift speed. So drift speed will be, okay, so if I look at some distance and divide by the time that the electron took to go over this distance, that would be the drift speed. So that's the average speed with which the electron is moving forward. Remember this, in this example that I gave, I am really going back and forth finally to get to the door. It's the distance divided by the total time it took me to get there. That's my drift speed. And it'll be a lot slower than the actual speed with which I was running. All right? And so it turns out that the actual drift speed is extremely small. This could be 10 to the power minus 4 to 10 to the power minus 5 meters per second. You can see how much slower it is and how much the motion of the electrons is getting impeded by these collisions with the ions. Is everybody appreciating this? So drift speed is a lot. So by the way, the fact that the electrons are colliding with these things, in this collision, do you think if these collisions are not elastic collisions, suppose it turns out to be inelastic, would there be some energy that is going to be lost in the form of, say, heat or something? Yeah, and that's why, and that energy loss is what gives rise to what is called resistance of a material. You will see, if you look at any electronic circuit, you'll see a lot of resistors, and those are really materials in which, all of the resistors are going to be metals or conductors. But the point is that the materials that have higher resistance, in those materials, there'll be more such collisions giving out heat energy. And so the material will heat up. If you pass current for some time and you touch it, it'll get heated up because of this resistance, this collision of the electrons with the ions. All right? And so we'll soon start talking about the resistance of the material. But basic mechanism you should keep in mind, it is due to the collision of the electrons with the ions that is producing the, and if this is inelastic, some of the kinetic energy of the electron will be converted into heat. And there will be this impediment to the motion of the electron because of the collision. Is that making sense? Okay, so everybody understands the word drift speed at this moment, right? Now what I want to do is do a very important thing, which is relate this drift speed to this thing called current density. And let's assume that this is true. That means current density is just current per unit area. We are going to assume that we have J is constant and it's for parallel to dA. So we'll assume mostly in this course that J is equal to I over A. Okay, so then how do I relate the drift speed to J? Not difficult at all. So relation between drift speed Okay, in order to do this, let's again look at this picture here. All right, if I'm looking at this picture, let's say that there's some electron, let's say this one. So this electron, there's an electron here, this one here. Let's say this electron was initially here, you know, at this near this cross section, and after some time it came here, and let's say this distance is L. I'm just picking 2 points, and I'm saying this electron was initially here, then it later came here. By the way, does everybody see why the electron is drifting at all, even after all this collision? It's because of the battery, right? The battery is always pushing it in a certain direction. So even though they keep colliding with the ions, keep moving back, moving back, moving back, on an average they're slowly crawling in a certain direction. Okay, so if suppose L is the distance between the, between say the position of the electron here and position of the electron here, and let's say that it took time t to get from say A to B. So this is the cross section A and this is the cross section, let me not call it A, let me give it small a and small b, because capital A we are using for area of cross section. So from A to B, then who wants to tell me how can I write the current? Or at least tell me first, instead of current, let's go slowly. How can I write charge? Now I will define one term, N, which is called charge density. And what is charge density? This is charge per unit volume. So that means, and here I'm only talking about, this is the charge density of free electrons. So in other words, what I'm talking about when I say charge, I mean charge of free electrons. So who wants to tell me how can I write Q, which is, how can I write Q, which is the charge, total charge of the free electrons in that volume. So this is the total charge of free electrons in the volume in terms of this N. Which volume are we talking about? The electron is going from point A to point B. The volume, that the area of cross section, this is A, and this is the volume we are talking about, right? Is everybody seeing that that's the volume we are talking about if the electron went from point A to point B? Wouldn't the charge be the number of electrons per unit volume, number of free electrons per unit volume, this thing, times what? Go ahead.
1.6 at the center of the vacuum.
Good. Times the charge of the electron times what? Because Q obviously have to, so yes, there is an E. This is the charge of one electron. This is the elementary charge. But what do I have to multiply? Volume, good. So the thing is, Q will be equal to number of electrons per unit volume times volume. This is the total number N, right? This gives you the total number in that volume. Is everybody appreciating that little n times the volume of this region will give me the total number of free electrons that are in this volume, right? And if I multiply the total number by E, wouldn't I get the total charge in that volume? No? Which part is confusing here?
Well, you said that N is the charge of 2 electrons over the volume, so if you put it into the equation, the volumes would cancel. And then
No, see, this is charge divided by volume, right?
Yeah.
So you can see here that from this relation, if I wanted to find charge of free electron, from this relation here, do you see if I wanted to find charge of free electron, I have to do n times volume. If I bring this here, n times volume, wouldn't that become charge of free electron?
What do you mean?
Sorry. Okay, that's a very good point. Actually, this is not charge of electron, this is number. Thank you very much. Very good point. This is number of free electrons. So number of free electrons will be little n times this volume, right? So then do you see that if this thing is the total number of free electrons, if I multiply it by the charge of 1 electron, that will give me the total charge in this volume. Thanks. Is this making sense, folks? All right, great. So if this is the case, who wants to tell me what is the volume of this region between point little a and point little b? So the electron has moved from here to here. What is the volume in terms of things that I gave you? I told you that this length is L, and I told you that the area of cross section is A, of this wire is A times L. Wouldn't it be the volume? Okay, so basically what we find then, you can see, I see that Q is equal to N volume times E, which can be written as Q is equal to N times A times L times E. Now here is the thing, I am interested in current. I know that current I is charge per unit time. How much charge of the electron flows per unit time? So that's going to be NALE divided by the time. But what is L over T? Is there a name for L over T? Go ahead. Very good. That's the drift speed. You know, the total distance that the electron moved divided by the time that it took, that's the drift speed, right? So the thing is, so L over T is what we call the drift speed. So I find that current is equal to NA drift speed V sub VD, V sub D, V drift times E. This is an important relation. It tells you how to find the current if you are given the area of cross section of the wire, if you are given the current density, if you are given the drift speed, and you know the elementary charge anyway. Using this, can somebody tell me how to find J, the current density? Let's say the magnitude of current density, isn't that I over A? If that's the case, J will be N VD times E. Just from here, is everybody seeing if you divide both sides by A, you get J? So basically the conclusions that we have come to so far are these. The first thing is that we have found that J, the magnitude of current density, is N times the drift speed. Yeah, this is the drift speed times the charge of an elementary particle like electron or proton. That's E, elementary charge, right? 1.6 times 10 power minus 19 coulomb, just like somebody pointed out. This is a fixed thing. Is everybody clear on this? Any questions about this? So do you see that you can find the current density if you're given the number of electrons per unit volume and if you're given the drift speed, right? I think I have a problem for you. So this problem is an example from your book which says, it may not be a solved example. This one says copper metal. So you're using copper wire, and copper has number of free electrons per unit volume. This is number of free electrons in copper per unit volume equal to 8.5 times 10 power 28 per meter cubed. Notice how many free electrons are there, 10 to the power 28 in each meter cubed, right? The question is, and you are given that the radius, this is a circular cross section wire, and the radius is 900 micrometer. This is the radius of wire. The current is given to you to be 17 milliamps. So that means this is 17 times 10 power minus 3 amperes. The question is asking you, what is the drift speed? Any thoughts on how you can find it? Everybody should take half a minute to talk to a person next to them. I'm going to pick one person and say, tell me how to find the drift speed. Is everybody clear on what the question is? You are given the number of electrons per unit volume. You are given the radius of the wire. You are given the current. Radius is this radius here. So if you cut this wire, you are given the radius of a circular wire. Tell me how to find the drift speed. Please talk to a person next to you. Okay, somebody from the second last row, please. Anybody from the second last row wants to help me figure out how to find the drift speed? Tell me the procedures. Go ahead, folks. This is a friendly class. Somebody? Oh, go ahead, please. Okay, so first you're saying find the area of cross section by doing pi r squared, right? That's the area of cross section. So A here will be pi times r squared. That will be the area of cross section of this wire. If I cut this circular wire, the area of cross section. Okay, good. Then what do I do?
Just plug in the values into the equation.
Right, you can use that, or you are absolutely correct. You can use even this NEVD, and you can say, oh, J I know is current per unit area, right? So J is I divided by A, and that's equal to NEVD. And what you're looking for is the drift speed. So from here you can see that the drift speed is going to be I divided by A divided by N times E. I'm not going to plug in the numbers. The current is given to you to be 17 milliamps. The area of cross section we found here. N is given to you, and E is well known. E is 1.6 times 10 power minus 19 coulomb. If everything is in SI unit, the answer should be in, what should be the unit? Meters per second, yeah. If everything is in SI unit. Any questions about this, folks? Anybody? Okay, is this idea clear? Okay, so then let's now move on to talking about a new concept. Again, you can see how many new concepts we have introduced. Current density, drift speed, number of charged particles per unit volume. Now I'm going to introduce a new concept which is called resistivity. And I already mentioned to you a little bit what will give rise to resistivity. Remember I told you when the electrons are trying to move, they'll run into these ions, and that collision will produce heat if it's not an elastic collision, right? And so do you see that this collision is producing resistance to the motion of electron? And that's what will give rise to resistivity. So how is this thing called resistivity, which we denote with a Greek symbol rho, defined. It turns out resistivity is defined as the magnitude of electric field divided by the current magnitude of current density. So this is the electric field, and this is the current density. This is the definition of resistivity. One way to see this is this. So what is E? For example, if you have a battery, does the battery have a potential difference across it? Yes, that's what we call voltage of the battery, that's 9 volts. If there is a potential difference, there must be an electric field, right? And this electric field is exerting a force on the electrons, which is trying to move them, accelerate them. That's the electric field that we are talking about. Now notice something interesting. If suppose you had some battery, let's say 9 volts battery, right? And you have some circuit here. In this circuit, let's say that the electric field is a certain value, fixed value, because you have a fixed battery, right? So electric field is fixed. The question is, what will happen if rho is more to the current density? Will it be less? Do you see that rho times J is equal to E? So if E is fixed, what does it mean? If rho increases, that means J decreases. Do you see that? So resistivity is inversely related to current density. Is that making sense? Because that's the thing. Resistivity is a measure of how much impediment there is to the motion of these free electrons when you apply an electric field. That means when you put a battery in the circuit, when you have a potential difference. That's force, that's exerting a force. This electric field will exert a force on the electron. Remember, this F is equal to QE. So each electron has a charge E. If you multiply it by the electric field that is produced by the battery, that will tell you how much is the force on the free electron, each free electron. But the question is, because of this material's resistivity, these electrons bumping into these ions and producing heat, the current will not always be the same. It will depend upon what kind of material you have, Does that make sense? So resistivity of a material is basically the ratio of E, the electric field that you're applying because of this battery, for example, to the current density. Higher is the resistivity, lower is the current density. By the way, in many materials, rho is a constant. And if rho is a constant, then this relation is what is called Ohm's law. So if rho is constant for a material, then this relation rho is equal to E over J is called Ohm's law. Another way to say it is E is equal to rho times J. All right. In this case, for example, for Ohm's law would say what? Suppose you apply an electric field, and this is J, right? This is the magnitude of electric field, this is the magnitude of J. What would Ohm's law tell you about this plot? Suppose you have different electric field, 1 Newton per coulomb, 2 Newton per coulomb, etc. What will the plot look like from Ohm's law? If the electric field is 0, J is 0. If electric fields become, say, something, this is increasing in a proportional fashion. Don't you see that this says that E is proportional to J, isn't it? Right? Is that making sense? So this curve will be a straight line passing through the origin. Does it make sense? Why is it origin? Because, well, when E is 0, J is 0. That's what this thing is saying. E is 0, you know, these two are 0, and then it takes off. Does that make sense, folks? So this is Ohm's law. Ohm's law basically gives you a plot like this. Now it turns out not every material follows Ohm's law. There are these things called, for example, semiconductors. You already probably are familiar with this in your engineering classes, that don't show this kind of a behavior. They may show a non-linear behavior in things, and those materials are called non-ohmic. You know, they are not following Ohm's law. Okay, now here is the thing. I want you to, maybe you have seen a form of Ohm's law that looks slightly different, because maybe it was not in terms of electric field, maybe it was in terms of potential difference, the voltage V of the battery, as opposed to the electric field that is applied by the battery. But you know that the two are related. How is the potential difference related to the electric field? Anybody? If suppose the electric field is constant, how can we turn Ohm's law into a form which looks more familiar to you, maybe from your high school class?
The difference of potential equals the electric field times the distance.
Very good. So what she's saying is absolutely correct, which is that we can turn Ohm's law into a form that you might be more familiar with from your high school by relating the potential difference to the electric field. Because remember, whenever there is a potential difference, there's an electric field, right? So remember this thing, V final minus V initial, or delta V, was equal to integral E dot dl. Remember, this is the relationship. And by the way, delta V is something that we are calling V now. We have changed our notation. We just keep calling it V, means potential difference. Okay? If the electric field is constant, do you see I can pull the E out and integral dl will just become L. So in that case, we can say that V is equal to E times L. Is this making sense? In other words, E would be equal to V divided by L. Right? So let's try to convert Ohm's law into a form that is more familiar to you. So I'm going to try to use this fact. This is how the potential difference is related to electric field. So what we learned already is that rho is equal to E over J. And so rho in terms of not the electric field but the potential difference. So for example, if it's a 3-volt battery, the potential difference will be 3 volts across the positive and negative terminal, right? Positive is 3 volt higher than the negative, that's this potential difference. I can write it as V divided by L times J. By the way, can we write J in terms of current? Because maybe you're more familiar with Ohm's law in terms of current, right? How is current density related to current? Anybody? J can be written as current per unit, sorry, current per unit area, isn't it? This area gets flipped, so it goes in the numerator. So what we are left with is V, and let me not worry about this magnitude. The point is that, I mean, I'm saying the potential difference, obviously one of the things is at a higher potential, the positive thing is at a higher potential, the negative thing is at a lower potential. We only care about the potential difference magnitude here, not which thing is higher and which thing is lower. So then it will be L times I. Is this making sense, folks? The other thing that we can do is, does anybody remember the form of Ohm's law in terms of potential difference V and the current I? What was it? From high school? Nobody has done Ohm's law? Go ahead. Okay, so he is saying that, recall that from high school physics, if you took it, V was equal to IR. In other words, something called resistance was equal to V divided by I. This R was called the resistance of the material. Okay, and when was it called Ohm's law? When resistance was a constant. So if the resistance of a material is constant, that means V is proportional to I. You would call this relation Ohm's law, right? The question is, what is the resistance if you look at connecting these two, I'm going to give you half a minute. Everybody should tell me what is the relationship between resistance and resistivity and the length of the wire and the area of cross section of the wire. Is everybody understanding the question? I want you to tell me the equation for resistance of the wire, the definition of resistance in terms of resistivity, the length of the wire, and the area of cross section. Please, everybody should be talking to a person next to them. All right, somebody from the third row, please. Anybody from the third row? R is equal to rho times what? L over A. Is everybody agreeing that that's what it is? And that's absolutely right, because you can see from here, from this relation, you can move the L here, you can move the A down. So this is rho L over A, and that is equal to V over I. And from what you learned in high school, the resistance of a material was defined of length L, and area of cross section A was defined as V divided by I. So you can see that R must be equal to rho L over A, right? So this is the relation between rho and R. Notice something interesting. The good thing about resistivity of a material is that you can find resistivity in a table. You know, you can go to the library, you can open the library book, and you will see it will tell you resistivity of a nichrome wire. This is a nichrome wire. It will tell you what is the resistivity of a nichrome wire at this temperature, at this temperature, at this temperature, etc. Resistance depends upon the length of the wire and the area of cross section. So resistance will keep changing depending upon how long your wire is. And what does it tell you? If the wire is longer, the resistance will be more, right? That means there's more impediment to the motion of the electrons in the wire if the wire is longer. It's harder for the electrons to get from one side to the other, even if you're applying an electric field or potential difference. If the area of cross section is more, is it easier for the electron to go from one side to the other? If there's more room to move from one side to the other? Yes. So higher is the area of cross section, lower is the resistance, right? So fatter wire has a lower resistance. On the other hand, as I said, resistivity of rho is a constant for a given material. At a given temperature. By the way, as I said, this relation R is equal to V over I is another way to write Ohm's law if R is constant. So that's another form. So Ohm's law also says R is equal to V over I. If this is a constant, then this is Ohm's law also. And in this case, again, if you're plotting, let me ask you, so suppose if I have V and we have I, suppose I keep applying a voltage, you know, battery is 1 volt battery or 2 volt battery or 3 volt battery or 4 volt battery. If the resistance of the material is constant, what would happen to the current? If there's no voltage, current is 0, right? And as the voltage increases, the current will increase, right? That's what this thing is saying. Is everybody seeing that what this says is I times R is equal to V? These are all different ways of writing Ohm's law. Is everybody appreciating this relation, this relation, this relation, this, all of this is Ohm's law, so long as resistivity and resistance are constants. They don't change, you know, when you apply different voltages, for example. Making sense? Yeah? Okay, so, and I want you to appreciate this fact that rho is constant for a material for a given temperature, but resistance depends upon the length and the area of cross section and on rho. Now, since I said rho depends upon temperature, how do you think rho will depend upon temperature? Anybody has any thoughts? Again, I want you to keep in your mind the fact that resistance and resistivity is really due to the electrons bumping into ions and that collision not being elastic and hence producing heat. That's what is giving rise to resistance of the material. What do you think will happen if you heat up a material? So I take this wire and I heat it up. Will the resistivity of this material go up or go down? Huh? How many people think it will go up? How many think it will go down? Okay, it turns out heating the material increases resistivity. It's all right. I mean, it's good to think about. And why is that? Think about it this way. It turns out that the electrons, the free electrons, if I put a battery across this wire and the electrons start to accelerate and they're bumping into these ions and colliding and producing heat, which is what gives rise to resistance, then again moving forward, colliding, moving back. Do you see that if the ions are in orderly fashion, if those positive chions, those heavy nuclei, if they are in orderly fashion in this metal, do you see it will be much easier for these electrons to maneuver around them? Wouldn't it? Think about it. If I'm running from here to there, and if I knew exactly who was sitting where, if everybody was in a very periodic fashion in this room, I could just move around and I'll find my way. But if things were totally chaotic here, I wouldn't know which way to move and I'll bump into people more. And what happens is that at lower and lower temperature, the ions are in much more orderly fashion, and as the temperature increases, the ions vibrate more and more. In fact, temperature is a measure of this motion of ions, right? And so the thing is, at higher and higher temperature, these ions will vibrate more and more and more and more and more, and because of that, the periodicity gets destroyed. And if the periodicity gets destroyed, the electrons are much more likely to collide with the ions when you connect the wire to a battery and this electric field is trying to push them in a certain direction. And so the point is, resistivity of the material will go up if you increase the temperature, because the probability of collision will increase because the periodicity gets destroyed, right? And if the resistivity goes up, obviously the resistance will go up too, because resistance is proportional to resistivity. Is this making sense, folks? So what is the exact relation? It's this. Resistivity at a temperature T is equal to resistivity at a temperature T0 plus alpha times T minus T0. What is alpha here? Alpha is called the temperature coefficient of resistivity. So basically, what we are trying to say is what we are trying to say here is that rho of T is equal to rho T0 plus alpha times delta T. What is delta T? Delta T is just T minus T0. So here it's just the change in temperature, T minus T0. And alpha typically is, that's what I'm saying, positive. Alpha is typically positive for a material, and that's why as the temperature, if T is more than T0, alpha is positive. So if T is greater than T0, rho of T is greater than rho T0. Is everybody seeing rho T is, the rho of T is the resistivity at temperature T, rho of T0 is the resistivity at temperature T0. And this is why I told you the physical mechanism. The physical reason for this is at higher and higher temperature, the periodicity is going to be worse and worse because of this vibration of ions, and hence the probability of colliding with the ions increases, and hence the resistivity increases as the temperature goes up. Right? Does this make sense? Okay, great. Now if this is the relation of resistivity, let's multiply throughout by L over A. So I get this L over A times rho of t is equal to L over A rho of T0 plus, sorry, by the way, both relations that I wrote here need fixing. So you can see my units are not working. This should be 1 plus alpha times this. Sorry about that. So this rho of T0 is a factor that goes with both terms here. So here also same thing. This is rho T0 1 plus this over the whole thing. Sorry about that. Okay. So the thing is, so this is all correct. So the thing is, so here what do we see? If I multiply throughout by L over A, I get this. All I'm doing is L over A on this side, L over A on this side. Can we give this thing a name? What would be a cool name for it? Harriet? No, we can think of a better name. What would be more instructive here? Can we call it resistance at temperature T? And what about this? Can we call it resistance at temperature T0? All those three things together? No? Okay. So basically what we find then, is that we can write resistance at temperature T in terms of resistance at temperature T0 like this. We can say resistance at temperature T is equal to resistance at temperature T0 1 plus alpha delta T. So if T is greater than T0, resistance at temperature T will be greater than resistance at T0. And I already told you it's because the collisions will be more because the periodicity is destroyed. Right? Any questions, folks? Okay, one thing that we didn't talk about is what do you think is the SI unit of resistance? Again, without naming any cool names, who wants to tell me from the 4th row what would be the unit of resistance in terms of things that you know? Go ahead, anybody? Look at this equation and tell me. The unit of resistance should be the unit of voltage or potential difference divided by unit of current, right? So this will be, go ahead please. Very good. The SI unit of resistance is volts per ampere and it's given a shorter name, it's called ohm. All right. So notice from here that, let me write it over here maybe, that the SI unit of resistance is volts per ampere and this has a shorter name ohm and it's written with this Greek symbol omega, capital omega. Ohm is easy to remember. You know, in Indian this thing you do meditation and you go om. So that's basically the sound of this thing. And again it's after a scientist, you know, some scientist who did experiment, his last name was Ohm. So to honor him, 1 volt divided by 1 volt divided by 1 amp is 1 ohm. Is that making sense, folks? Anybody has any questions here? All right, then the next thing that we want to do is we want to find an expression for resistivity in terms of this time between collisions. So I already told you that resistivity is due to this impediment to the motion of the electrons, right? So electrons keep bumping. So let's say that tau is the average time between collision. The question is, can we find a relation for resistivity in terms of the time between collision and the number of electrons per unit volume? So let's find the relation between, and by the way, typically I have seen again that this idea is very difficult somehow in the exam. So if I give anything related to this, I want you to think about it right now because somehow this turns out to be very difficult. Also, I want you to note that Ohm's law, you know, if I ask you in the exam, does the resistance of a material depend upon, for we are going to assume in this class that we are only dealing with those materials that are ohmic, that means they follow Ohm's law. And if I say if the current increases, will the resistance of the material change? What would you say? The answer is no. Why? Because even though R is equal to V over I, this is Ohm's law, if the current increases, the voltage must have increased correspondingly such that the ratio of the two should be constant, right? Because you can see R only depends upon the properties of the resistor. In fact, materials that have resistance, you know, all real materials will have resistance unless you're talking about, say, superconductors or something. Those are the only materials that will have zero resistance. Otherwise, you have to go to zero temperature, you know, for you to have a complete periodicity of the lattice, because that's by zero temperature I mean absolute zero Kelvin. At that temperature, you know, all these ions stop vibrating and the system becomes very periodic. But the point is, in a superconducting material, there's some very interesting and weird effects that take place, because of which the resistance becomes zero even at finite temperature. Isn't that very interesting? And nowadays people have found these things called, you know, like in 1985 they discovered these high temperature superconductors. And you know what is so great about high temperature superconductors? They show superconductivity at temperatures more than, say, 100 Kelvin or something. Imagine if we were able to make materials that were superconductors, that means resistance was zero, resistance was really zero at room temperature. Room temperature is, say, you know, 300 Kelvin. What would that be really good? Why would it be good? What's the problem with resistance? What's the bad thing about resistance? Go ahead. It generates heat. So one of the things is we are wasting so much energy, electrical energy, in the form of heat, right? It's just getting wasted. For example, when the energy comes from the power station, when the power stations are generating electricity and they're sending it to our house, do you know that 30 to 40% of the power just gets wasted in the form of heat in the wires? And that's considered fine, because you could lose more if you're not careful. So 30 to 40% of the wastage just in the power line coming from, say, Chicago to Pittsburgh, if we are getting power from, say, some company in Chicago, is just due to the heat. So imagine how much energy we would save if we could make those wires superconducting, right? Because those wires are made of copper, which have extremely small resistance, but it doesn't matter. So what I mean is extremely small resistivity. But hey, if it's very long wire, the resistance would be very large, right? R is equal to rho L over A. So you still lose a lot of power, and that is a bad thing. So heating could also be a problem for electronic circuit, because you have these resistors which have resistance in electronic circuits. And again, if you pass high current and there's too much heating, the wires could melt, right? And that wouldn't be good. So it actually puts a limit. The heating puts a limit on how close you can put different elements on an electronic circuit. So heating in that sense is not a helpful thing. But I want to point your attention to the fact is R is equal to rho L over A. So R does not depend on V or I. It depends upon, you know, so if V increases, I will increase correspondingly so that R is constant, right? Any questions about this? Anybody? All right, then I want now to tell you about the relationship between resistivity and tau, where tau is defined as time between collisions. So here is the thing. We are talking, this is my wire, I'm just blowing it up. Let's say there's some current flowing in this direction, this is my current. Let's look at some area of cross section which has area of this wire that has area A. And we are saying electrons are moving, say, this way, and then they bump into the ion, they move back, then they bump into another ion, they move like this, etc. Right? The thing is, this tau is the average time, not time, but average time between two collisions. Now here is the thing, if there is a current flowing, obviously there must be some force on the electron, and if you remember from physics 1, from Newton's second law, the net force on the electron should be Newton's second law, mass times acceleration, right? Mass times the acceleration. But here what kind of force are we talking about? What kind of force are the electrons feeling? So let me put this thing in a circuit. So this is the way the circuit looks like, right? So the electrons are moving like this. I'm just showing you a blown up view of this wire here, okay? So the point is the electrons are moving here like this. Why are they accelerating? Why would they be feeling a force in a certain direction? It's because of the battery, right? So the potential difference of the battery creates an electric field, and so the force on the electron will be Q times E, the electric field. Isn't it? F is equal to, F is equal to QE for this case because we are talking about force due to electric field. F is equal to ma is always true in classical physics from Newton's second law. So these two things are definitely true. Let's not worry about the directions right now, so let's just worry about the magnitude. Okay, so here is the thing. If suppose you assume that because of these collisions the electrons keep moving very slowly forward, and there is an average speed which we call the drift speed, right, with which they are drifting, overall you can think that the electrons are drifting in a certain direction with the speed, the drift speed. And if we assume that overall the electrons move with a, with this drift speed, we can say, okay, so before we connected this thing to a battery, maybe the speed of the electron was 0, and then once we closed the switch, the electrons started drifting with this speed, the drift speed. Do you remember? We can say this, V final is equal to V initial plus the acceleration times time. Isn't this what you learned from equation of kinematics for constant acceleration? Do you remember from physics 1? V final was V initial plus A times T. A was the acceleration and T is the time. In our case, initially these things are at rest. So for us, we started out when this thing was open, it was at rest, and then finally this is the drift speed, and T is the time between collisions. So we have Vd is equal to A times the time between collision tau. What I'm going to do is I am going to make use of this relation and also the definition of resistivity in terms of electric field. Do you remember a long time ago how the resistivity was defined in terms of electric field? Anybody? Go ahead folks, anybody? Do you remember this resistivity? The first thing we did was defined it in terms of E over J, didn't we? Okay, so if that's the case, then we know that E should be equal to rho times J. We also learned that J, recall that J has a magnitude which is N times E times V sub D. Do you remember that? This is something that we derived in this class, and so instead of J here, I can write N E V sub D. This is equal to E. Let's say this is the magnitude. Is everybody with me? Okay, then I am going to go back to this particular relation, F is equal to ma, and in this case the force is electrostatic, electrical. It's due to the electric field, so F is equal to QE. So now what I'm going to do is E times E, this electric field will be this, rho N times E. So E times E is equal to mass times acceleration. Instead of acceleration, can I write Vd over tau from here? Okay, so I'm going to write here Vd divided by tau. Is everybody comfortable with this? Hey, what are we going to get here? Look, we got something really interesting. Rho is equal to m Vd divided by, haven't I missed a drift speed somewhere? Yeah, I missed this one. Remember, E is Ne rho Ne Vd. So I have here E is equal to rho Ne, and there is a Vd here, and this is equal to this, right? So do you see that from both sides Vd gets cancelled? Yeah? So what I'm left with is this, rho is equal to m divided by tau divided by n times E square. And this is the relationship between resistivity of a material, mass of the electron, which you know, time between collision that you can look up for different particles at different temperatures. It'll change, right? As the temperature goes up, what will happen to tau? Will the collisions become more frequent as the temperature goes up because the periodicity gets destroyed? So tau will decrease, and tau decreases means rho will increase. So the resistivity will increase because there will be more, easily carried out collisions. N is the number of electrons per unit volume. You can see that there are more electrons per unit volume, that material will have lower resistivity, right? Do you see a good conductor? A good conductor will be a conductor which has a lot of free electrons like copper. So those materials will have very low resistivity. So even though I gave you this example and I said to you that even though they are using copper wires to send electricity from the powerhouse to our house, we lose 30 to 40% of it. In this course, we are going to assume that all of our wires are made of copper. All of these wires, these things are made of copper, and we are going to assume that unless we explicitly show something else put in the circuit, the wires don't have any resistance. In other words, these are such small wires that we are going to ignore their resistance unless we actually explicitly show some resistance like this. So we are going to show resistance in the circuit explicitly by putting some jagged line, and maybe that jagged line is some other conductor, which might have less N. So this conductor here that we are talking about might have, say, smaller N number of electrons per unit volume, so its resistivity might be higher. Do you know what I'm saying? And so those kinds of materials will be the ones that we are going to use for our resistors. Because remember, even though we are talking about resistors, are we still talking about conductors? Are all of those jagged things still conductors? Because what will be the resistivity of an insulator, say chalk? Yeah, it will be almost infinite, right? Even if I connect it to a battery, do you think the electrons are going to, there's no free electron here, right? Unless you have electrical breakdown or something which will be extremely high for these kinds of materials. For air, the electrical breakdown is 3 times 10 power 6 newtons per coulomb, but we are not talking about that kind of voltage. So these insulators, even though I say resistivity depends upon how many free electrons per unit volume, I'm not saying we are talking about insulators. These are still conductors. The things that we are going to start calling resistance are still conductors, but the number of free electrons per unit volume is very small, and so rho will be larger, right? And hence the resistance will be larger for those materials. Is that making sense? Because insulators would mean N, that N is 0, that means rho is infinite. That's not what we are talking about. Is everybody clear, please?
M we're using mass of what?
Yeah, M is the mass of an electron. So M is constant. Notice here, this is very interesting because what it says, resistivity, and this is a question that I often give as a multiple choice in the test or something, saying resistivity of a material depends upon, and then I ask, does it depend upon the electric field? Does it depend upon J? Does it depend upon time between collision? And does it depend upon number of electrons per unit volume? And what is the answer? Which of the things does it depend upon? Resistivity of a material. Anybody? Because this is one of my favorite questions to ask. What is the answer to this question? Anybody? Go ahead, please. Number of electrons per unit volume and time between collision. Those are the only things. So this is really the relation between rho, tau, and N. So if you have more electrons per unit volume, rho will be less. if you have more time between collision, rho will be less. Rho does not depend upon E or J, because if the electric field is higher, if your battery has a high voltage and has a higher electric field, is applying a higher electric field, J will increase such that this ratio stays this. So for a given material at a given temperature, rho will be fixed. Now what do you think, is that making sense to everybody? I think this is important to understand, that rho does not depend upon which battery you are using in the circuit. Why? Because if you use a battery which will apply a larger electric field, the current density will be more, such that the ratio stays that. On the other hand, will rho depend upon temperature? Why does rho depend upon temperature? Anybody? Which thing changes as temperature changes? Yeah, the time is the one that is significantly changing. You know, n, number of electrons per unit volume, will change very little with temperature. So when I tell you this, when I say rho at a higher temperature is more, that's because the periodicity of the lattice is described, the periodicity of the ions is described, is destroyed, and hence the time between the collision becomes shorter, right? That tau will change, and that's why resistivity depends upon temperature. Does it make sense? Anybody has a question about this? So everybody comfortable with this? All right, then the last topic from this chapter was a very short chapter, by the way. So we started today and we are going to end it today. So the thing is, the last topic from this chapter is related to power. Now I want you, I don't want to do all the work, you remind us, somebody here should be reminding everybody, what is the definition of power? Go ahead, please. Excellent. Power can be defined as how much is the work done by something per unit time, right? For example, you know, you go to a car dealer and they tell you, oh, this car is this many horsepower. Of course, horsepower is not SI unit. The SI unit of power, power would be what? Joules per second, right? So the thing is, joules per second is the SI unit of power, right? Because how much energy, but basically when they say, oh, this is this many horsepower, that is that many horsepower, basically what they're saying, how much time does it take, for example, the car to go from 0 speed to certain speed? You know, how fast is the work done to accelerate it from a certain, from 0 speed to say certain speed? So cars that go faster, sports car might be higher horsepower, right? Because it's important how fast the work is being done. Now, power can also be defined as the energy per unit time, right? Work done per unit time or the energy per unit time. So one kind of power that we should be talking about is how much is the power that is given out by a battery. Is that a fair question? How much is the power that is given out by a battery? So suppose I have a circuit like this, okay? Let's say that the battery voltage is V. The resistance in this circuit is R, and I said we are going to always put resistance explicitly. This is some wire, and let's say that there is some current flowing here, and we said current always flows. We show the direction of current as opposite to the direction of flow of electron. However, current is really the total number of electrons moving through any cross section, so total charge of the electron flowing through any cross section every second, right? It's Q over T. So the point here is, can we figure out how much is the power given out by the battery? Is it easy? Okay, it is easy, and here is how you'll do it. So power output of a battery, I'm going to write, P out as power output. And power output of battery, we can figure out, the question is, what is it? And we already know that power is equal to energy per unit time, or you can define it as work done by something per unit time, right? So another way to say it is we can say work done by some agency on something is equal to power times time. Now work done, let's say that we have some infinitesimal work done. Do you remember that infinitesimal work done can be written as negative of the change in potential energy? I'm not going to worry about negative sign and positive sign, that's not what I'm interested in. So I'm just going to write it as change in potential energy. Is this something that rings a bell from Physics 1 and Physics 2? This is something you have done in both courses. Okay, so then dW should be Q times change in potential. And by the way, change in potential is what we call voltage, right? Is this making sense? So basically, and let's say that we are talking, so let's say we are talking about a very small charge that moves. Sorry. Just give me a few minutes. So then what we have here is that dW is equal to, what is current, folks? Do we know what current is? Current is dq over dt, right? So if you like, I can write dq as I dt. So then I have dW is equal, instead of dq, I'm going to write I times dt, and delta V, remember the new name that we have for potential difference, what do we call it? Just V. These days we are just calling the potential difference across the battery. We no longer call it delta V, we just call it V. This is our new name, so this is V. So then what would be power? Is the rate of work done, right? dW over dt, the derivative of work done with respect to time. What is it? What is dW over dt from here? I times V. And so this is the power output of a battery. Power output of a battery is the current times the potential difference of the battery. So if you know how many volts the battery is, and you know what is the current, you can figure out the power output. Wait, this is not it. Now the second thing that we need to talk about is how much is the power that is dissipated in the form of heat in the resistance. Rate of heat produced, right? So that is the rate at which energy is being lost in the resistor. I'm just writing the rate of heat produced, all right? So the second thing that we want to know is what is the power dissipated in the form of heat in resistors, in a resistor. Let's say resistor has resistance R. Is it easy also? Yeah, power dissipated in the form of heat, you can write it as I times V, but then you have to realize if we need to figure out what is the power dissipated, we can do one thing. We can either write I in terms of R or V in terms of R. Let's make use of Ohm's law. Ohm's law says V is equal to I times R, right? If R is constant, this is Ohm's law. So if we make use of this, what will be power dissipated? Tell me, folks, can I write it as I? Instead of V, can I write I times R? Isn't it? And so this will be I square R. So if you have a resistance R, and if you know the current in the circuit, you can figure out how much is the energy that is being converted into heat every second by finding I square R. That's the energy that is being converted in the form of heat every second. It's easy to remember. Twinkle, twinkle, little star, power is equal to I square R, right? Okay, can you find this thing in terms of potential? Can you write this in terms of voltage, folks? Yeah. Another way to write the same thing will be like this. You can say power dissipated will be, instead of I, can I write it as V over R? So I can write it as V over R times V, which is V square times R, V square divided by R. So notice both of these are okay formulas to use. They're both correct equations to use for power dissipated. You can either use I square times R or V square divided by R, depending upon whether you know the current easily or the voltage easily. So for example, in a parallel circuit, you would often maybe know the voltage much more easily. So if you know voltage easily, then you might be able to use V square divided by R to calculate the power dissipated in the form of heat. Have a great day, folks. I'll see you guys next week.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.